Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on antenna. On my previous discussion on the part 16, okay, I have briefly discussed on the antenna radiation. So basically, this is actually a continue, okay, based on the previous discussion. This video, I will focus again on the antenna radiation mechanism, okay, by the three very common type of antenna. The first one will be the single wire, two wire, and last but not least, dipole antenna. Okay, so basically this video again, okay, I'm going to focus how antenna actually radiate up the electromagnetic wave into the environment. So basically this will be the objective of this video. This will be the part 17 series discussion on antenna. So guys, if you're keen to know more about antenna, okay, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on antenna. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Before I continue, I'd like to urge you guys to help this channel by like this video. Okay, when more you guys actually help to like this video will have a better chances to reach up to a larger audience. So guys, help me. Give me a few seconds. Help me to press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. This is always one of the first few questions that we always ask concerning antenna is how is radiation accomplished? Okay, so in another word, okay, how are the EM field actually generated by the source contained and then later on guide within the transmission line and finally to the antenna and how they actually detach from the antenna, okay, to the free space wave. So basically, this is always a miss. Okay, we are not sure about all this. So hopefully with this video, okay, you can fully understand on the antenna radiation mechanism. Okay, so the best explanation can be provided through an illustration. Okay, however, okay, let us first examine some basic source of radiation. Okay, from the single wire. Okay, so basically this is a single wire. From the two wire. Okay, so basically this is from the two wire, one, two, and last but not least from the dipole antenna. Okay, so basically this video I'm going to focus on the three basic source of radiation from the single wire, two wire, and dipole antenna. Let's come to this diagram here. Okay, so before we come into the discussion on the so-called single wire, two wire, or dipole, okay, let's understand this better. Okay, so let me give you an example, okay, on this dipole antenna radiation so that you will actually aid you into understand the antenna radiation mechanism. Okay, so this is a receiving antenna. Okay, so this receiving half wave dipole antenna. Okay, basically they consist of two metal rods. Okay, so you can see that this is one metal rod. This is the second metal rod. So they consist of two metal rod. They are actually connected to a receiver. Okay, you can see that they are actually connected to a receiver. Okay, so typically this is actually a receiver diagram. The electric field, okay, which is the green arrow, as you can see that, you can see this green arrow. Okay, so of the incoming wave, push the electron on the rod back and forth. Okay, so you can see over here, okay, because of the electric field, you can see that, okay, this actually toggle from the plus to the minus, etc. So this is what it means. Okay, because of the electric field, okay, you can see that, okay, basically from this current, you can see that they flow out and also flow in. So this is what it means. So they actually push the electron on the rod back and forth and causing the end become alternative positive charge and negative charge. As you can see from here, now it's negative, now it's positive. So you can see that, okay, because of the changing, okay, of the electric field, okay, so basically you can see that the current also flow in different direction. Okay, this actually change the so-called the edge, either positive and negative. So this is what it actually described in green. Since the length of the antenna is half the wavelength of the wave, okay, the oscillating electric field induce standing wave of voltage, which is red in color. Okay, because with the electric field, you actually have this VSWR standing wave, okay, which is in red, and also the current in the rod. Okay, so basically you can see that current also start to flow. So they have two direction. Okay, so they either flow to or from the so-called rod over here. Okay, the oscillator current, okay, which is the black arrow, okay, they flow through the transmission line and into the receiver. Okay, so from here you can see that how does it flow. You can see from here, you can see that they flow out and they also flow into the receiver. So same on the other side. So basically this is what is actually described in blue over here. Okay, so with this you have a better idea. So now we are ready to discuss on the antenna radiation, firstly by the single wire first. Okay, so I don't want to dwell so much on the so-called derivation of the formula, okay, for this video here. So basically, you can see that this is actually a radiation mechanism equation. Okay, so we don't dwell so much. Okay, we will quickly understand this equation here. Okay, so it simply states that to cause radiation, okay, there must be a time vary current. Okay, so basically from here you can see that the current change with time. So basically this is what I mean. You must have this first criteria, the time vary current or an acceleration of charge. Okay, so basically you can see over here, okay, it's either acceleration of charge or deceleration of charge. You actually can have radiation mechanism. So from here you can see that, okay, firstly, the current change with time. Okay, if not, okay, the so-called the velocity of the charge actually change, increase or decrease, this actually will so-called incur radiation. Okay, so a single antenna radiate EM wave through the oscillator of electric current along its line. Okay, so basically this is a very simplified explanation of the process. Okay, so this video, for a start, we focus on the single line. Okay, how does the single line actually release the EM wave into the environment? Okay, first one will be on the current oscillation. Okay, so when an alternating current signal is applied to the single wire antenna, okay, it causes electron to oscillate back and forth along the wire. Okay, so imagine this, you actually has this AC source. Okay, on my earlier on discussion, you can see that because of the source, you actually create a E field. Okay, this actually causes the electron to oscillate back and forth along the wire, as you can see based on the earlier on discussion on this video here. Okay, so it's the same principle. Okay, because of the alternative E field, they actually cause the electron to oscillate back and forth along the wire. Okay, so this oscillation generate a time vary electric field along the wire. Okay, so basically this is what it mean here. Okay, so basically electrons start to move, and because once the electromagnetic electrons start to move, okay, it actually create this time vary electric field, and then therefore the rest I will discuss. So basically, let's focus on this magnetic field generation. Okay, the oscillating electric current also produce a time vary magnetic field around the wire as described by the Ampere law. Okay, so basically this is an additional of Maxwell equation. Okay, the magnetic field is perpendicular to the direction of the current flow. Okay, so if you remember earlier on discussion, the current flow along the conductor, okay, either they can flow this way or back. Okay, so basically this is what I mean. The magnetic field is so-called released perpendicular to the direction of the current flow. Let's say the current flow, so basically they release perpendicular to the direction of the current flow. Next, on the third, on the electromagnetic wave formation, okay, the time vary electric and magnetic field are coupled and propagate away from the antenna as an electromagnetic wave. Okay, so basically this is the antenna. So you can see that the EMF actually propagate away from the antenna. Okay, so this is described by Maxwell equations, okay, which show that a changing electric field induce a magnetic field, and then a changing magnetic field actually induce an electric field. Okay, so let's not dwell so much on this, but let me give you a simple example. Okay, so you need to have both the E and also the H field in order for the EM wave to propagate. Okay, remember early on we have discussed what E field cross the H field. Okay, remember the right hand rule, for example. Okay, you need to have both the E and the H, then they will be able to propagate. And then according to the Maxwell equation, okay, which means that any changing electric field, they actually induce a magnetic field. And once we have a changing magnetic field, this also in terms of induce an electric field. So basically, you can imagine that this change and then change, etc. So therefore, the E field and the magnetic field always change with time, and therefore the EM wave is able to release into the environment. Come to the radiation pattern. Okay, the radiation pattern of a single wire antenna actually depend on its length relative to the wavelength of the signal. Okay, so let's say if the if the wire is half of wavelength long, okay, so which is a very common design for dipole antenna. Okay, so on a dipole antenna, I will describe more. Okay, so it will radiate efficiently in a direction that is roughly omnidirection in the plane that is actually perpendicular to the wire. Okay, so basically, if you need to understand, okay, you can also see the video on the radiation pattern. Okay, but in short, if the length is so-called half of wavelength long, then it will be like a omnidirection antenna. So basically, they radiate out in a form of omnidirection radiation. Next, okay, let's quickly understand. Okay, so basically, how does EM wave actually release under some situation? Okay, so if a charge is not moving, okay, which means that there's no charge, okay, or there's no changes of charge, or the charge is not moving, the current is not created, and there's no radiation. So for a start, we must have a charge. Okay, if the charge is not moving, okay, so basically, because the charge is not moving, and then we don't have current, and hence because of this, we don't have any radiation. Next, okay, if a charge is moving, okay, and then they have a uniform velocity, which means that they maintain a constant speed. Okay, so there is no radiation. Okay, if the wire is straight and infinite in extent, okay, which means that the wire is infinite long. Okay, so there will not be having any form of radiation. Okay, so basically this is one of the condition. Okay, there will be radiation. Okay, if the wire is curved. Okay, basically from this part here, you can see that the wire is curved, then you will have some radiation. If there is a band, okay, again, you have some form of radiation, and you have some form of discontinuity. Okay, again, you also so-called will have some form of radiation here. Okay, so if charge is oscillating in a time motion, okay, it radiate even okay if the wire is straight. Okay, so basically this is the condition. Okay, how we can have so-called radiation. Okay, firstly, without any charge moving, okay, we don't have any radiation. So next, okay, if the charge is moving, okay, so let's say we have infinite length, okay, which means that the wire is very, very long, and then they are all straight, then we will not have any form of radiation. Okay, we will have some form of radiation. Okay, if the wire is curved, if the wire is bent, or the wire is so-called discontinued. Okay, which means that one thinner, one thicker. Okay, so basically you create a discontinuity, and this part here you actually will have some form of radiation also. Next, okay, so come to the impedance matching. Okay, for efficient radiation, the antenna impedance should be matched to the transmission line feeding it. Okay, so this ensure maximum power transfer from the transmitter to the antenna. Okay, so basically you can see that this is actually the transmission line. Okay, so basically the characteristic of the transmission line, okay, we want to design the antenna to match into the characteristics of the transmission line. And once we're able to do this, we actually ensure maximum power transfer, okay, from the transmitter to the antenna. Next, on the polarization, okay, the polarization of the radiate wave is actually determined by the orientation of the wire. Okay, for example, when we actually have a horizontal wire, okay, let's say this part here, okay, we have this horizontal wire. Okay, the E field is primarily horizontal, which means this part. So therefore, they actually result in a horizontal polarization wave. Okay, so basically this is the meaning here. Okay, on the single wire. Okay, so let's do a little bit deep in terms of understanding how does the EM wave actually release from a single wire. Okay, so a qualitative understanding of the radiate mechanism may be obtained by consider a pulse source attached to an open-end conducting wire which may be connected to the ground through a discrete load at its open end. Okay, so basically this paragraph here is shown in this diagram here. Okay, so basically you can see that this is basically a wire, single wire antenna. So basically they connect to a load and then to the ground. Okay, so basically this is actually driven by a power source here, as illustrated here. So when the wire is initially energized, okay, so basically you put a source and energize on the wire. Okay, the charge, okay, which is the free electron in the wire, okay, basically they set in motion. Okay, basically they start to vibrate, and they are actually have some motion, okay, by the electrical line of force that is created by the source. Okay, when charge are accelerate at the source end of the wire, okay, and also decelerate because of the reflection. Okay, so imagine this, you create a source here. So all the so-called free electron, they actually start to vibrate and they start to have some form of motion. And then they basically will move from here to the other end. And then after they reach over here, okay, they actually will have some reflection purpose. And because of the reflection, they actually cause some form of decelerate, which means that the speed, okay, basically will not be that fast because you actually have some reflection. Okay, so basically this is what I mean here. Okay, when charge accelerate at the source end of the wire, okay, so basically they are all accelerate at the source end, and then they basically will be decelerate, okay, because of reflection from its end. Okay, so basically you have reflection, okay, and then the speed will be reduced. Okay, so it is suggests that the radiate field are produced at each end and also along the remaining part of the wire. So you can imagine that basically you have some form of radiation here, you have some form of radiation here, and also along the line, you also have some form of radiation. Okay, next, okay, the stronger radiation with a broader frequency spectrum. Okay, which means that how to have a stronger radiation, which means a stronger EM wave. Okay, so also a broader frequency spectrum, a higher bandwidth actually occur. Okay, if the pulse are of shorter or more compact duration. So imagine, okay, so basically I don't have a so-called example here, but imagine the pulse is so-called narrow, much narrow, and you have more pulse. Okay, so basically when you have a shorter pulse or more compact pulse, okay, while continuous time vary, okay, so you just imagine earlier on I did mention about the EM wave. So basically you have a so-called a compact one. Okay, so basically this will actually create, okay, let's say the source is actually a continuous time harmonics, okay, which means that a sine wave. They oscillate charge ideally produce radiation of a single frequency that is determined by the frequency of oscillation. Okay, this will be a pulse. You can also imagine that, let's say, a sine wave. Okay, so basically, a sine wave will typically have a single frequency. Okay, so basically, this is the difference as compared to the pulse. The acceleration of the charge is actually achieved by an external source. Okay, so basically this is an external source. Okay, how does the charge actually so-called get their so-called energy and start to vibrate and start to have motion is basically by the external source. Okay, which apply force to set the charge in motion and generate the associated radiate field. Okay, the deceleration of the charge at the end of the wire is caused by internal force that is related to the induced field resulting from the build-up of charge concentrate at the wire ends. Okay, so basically, let's come to the last slide here. Okay, on the single wire. Okay, the internal force actually receive energy from the charge build-up as its velocity is reduced to zero at the end of the wire. Okay, so what does it mean? Okay, this means that the internal force, okay, basically they receive the energy from the charge build-up. Okay, so the velocity actually come to zero when they actually reach at the end of the wire. Okay, so therefore, charge acceleration due to an exciting electric field and desaturation due to impedance discontinuity or smooth curve of the wire are mechanism that is responsible for EM radiation. Okay, while both current density and charge density appeared as source term in Maxwell equation, charges is viewed as a more fundamental quantities, especially for transient field. Okay, even though this interpretation of radiation is primarily used for transient, okay, it can be also used to explain steady state radiation. Okay, so basically this is on a single wire. So hopefully with this you have a better idea how does a single wire actually release the EM wave to the environment. Okay, let's come to the two wire. Okay, so let us consider, okay, a voltage source. Okay, so basically you can see that a voltage source that is actually connected to a two conductor transmission line. Okay, so this is one conductor transmission line. This is another conductor transmission line. So this is what I mean. A voltage source actually connected to a two conductor transmission line, which is connected to an antenna. Okay, so basically they are connected to the antenna over here. Okay, they are connected to the antenna. Okay, so applying a voltage across the two conductor transmission line actually create an E field, as you can see from here. Okay, so basically you have so-called the E different. Okay, once you have the voltage different, okay, you actually create this E field between the two conductor. Okay, the electric field has associated with its electrical lines of force, which are tangible to the electric field at each point, and their strength is proportional to the electric field intensity. Okay, let's do a little bit understanding on the two-wire antenna radiation. Come to the current distribution. Okay, so a two-wire antenna typically consists of two conductive elements, which I have explained earlier on, and when they are actually fed with an AC signal at the center, as you can see from here, when the AC signal is applied, the electron oscillate back and forth. So basically the electron actually oscillate back and forth along the length of the wire. So basically this is what I mean. So basically they oscillate back and forth on the length of the wire. This actually create a time vary current distribution. The electric and magnetic field. So the oscillating current actually generate a time vary magnetic field around the wire as described by the Ampere's law. Simultaneously, the voltage difference between the two wires actually create an E field, which I have illustrated earlier on. Electromagnetic wave generation. So according to Maxwell equation, a time vary electric field induce a magnetic field. So basically, any changes in the E field, you actually induce a magnetic field. And when the magnetic field change, you also induce an electric field, which I have illustrated on the so-called one wire, single wire antenna. So this independent electric and magnetic field actually propagate away from the antenna as an EM wave. So basically this is how the EM wave propagate further and further away from the antenna. On the radiation pattern, the radiation pattern of a two-wire antenna actually depend on the length of the wire relative to the wavelength of the signal. So for example, for a half-wave dipole, so which means that each wire is lambda over 4 long, the radiation is maximum perpendicular to the axis of the wire and minimum along the axis. So basically, I have discussed on the so-called dipole radiation. So basically, you have a better idea. If not, you can always look at my earlier on video to understand this part here. On the resonance and efficiency, the antenna is most efficient when it is actually resonant, which means that the length is multiple of half a wavelength of the operating frequency. So at resonance, the impedance of the antenna is purely resistivity. So all the imaginary part will be ignored. So therefore, with this, you actually minimize energy loss and you actually maximize radiation. So again, I have discussed on the equivalent diagram of the antenna earlier on. So this actually make the antenna, basically efficient, once it is so-called resonant. Far field propagation in the far field region, which is on, again, I have done a video, when the so-called is considered a far field. So once it is actually at the far field, the EM wave will propagate as plane wave, which means that they have merged into 377 ohm, as a plane wave, with the electric and magnetic field, which is perpendicular to each other and to the direction of propagation. You always need to keep this in mind. You need to have both the E and H field in order for them to propagate. So basically, once they propagate into a far field, they become like a plane wave. So basically, under the near field, then you can say that it actually dominated by E or H. But once it propagate into the far field, it become a plane wave. So which means that they actually will be so-called the E and H, they will be perpendicular to each other, 90 degrees to each other. And basically, if you still remember, the E cross H will give us the direction of propagation. Now let's quickly come to the dipole antenna. So this diagram here actually show the dipole antenna. So the figure actually display the line of force which is generated between the arms of a small center fed dipole during the first quarter of the period. So keep this in mind. So let's say this is a sine wave. So basically you cut them into 4 pieces of sine wave. Which means that you can see that from the 0 point, they reach the maximum. So basically, we are actually at the maximum here. So this is what it means. The figure displays the line of force that is generated between the arms of a small center field dipole during the first quarter of the period. At this point, the charge reached its maximum value. As I mentioned earlier on, from 0 all the way to the maximum value, assume, so basically it's a sine time variation. And the line have traveled upward to a radiation distance of lambda over 4. So basically we have a quarter. So basically you can imagine that they actually have traveled, at a distance of lambda over 4. So in this example, let us assume that three lines are formed. Okay, basically once it reached lambda over 4, okay, let's assume that we actually find these three lines. So this is what I mean. Three lines are actually formed. Okay, so once it at so-called lambda over 4. Okay, next, okay, we are going to study, okay, when the period become t over 2. Okay, so it become lambda over 2. Okay, so earlier on was lambda over 4. So now we are going to consider lambda over 2. Okay, during the next quarter of the period, okay, the original tree line actually travel an additional lambda over 4. Okay, so earlier on the tree line, okay, if you still remember, these are all the earlier on tree line. So next is they are going to have more lines. I come to this later on. Okay, during the next quarter of the period, the original tree line actually travel an additional lambda over 4. Earlier on, from one lambda over 4, they travel another lambda over 4. So total lambda over 2 from the initial point. Okay, so as a result, the charge density of the conductors began to decrease. Okay, so this reduction can be understood as the effect of introducing opposite charge. If you still remember the plus and minus, so basically the direction keep on changing. Okay, so which by the end of the first half of the period neutralize the charge on the conductor. Okay, the line of force that is actually generated by this opposite charge also number 3. Okay, so basically they have also 3 line. Okay, also travel a distance of lambda over 4 during the second quarter of the first half. Okay, so this line are represent as dashed line in the figure. Okay, so these are all the early on line. So if you remember, these are all the early on line. Okay, so these are all the solid line. Okay, so basically these are all the early on. Okay, which means that which is at the quarter. So next, when we actually have the so-called lambda over 2, so these are the newly generated line. So this is what I mean. So in total, they actually travel lambda over 2. Okay, so basically this is what you want to mention. Okay, for this period here. So the end result is that there are actually 3 line of force pointing upward in the first lambda over 4. Okay, so basically, let's take a look on this here. So we actually have this upward, okay, and also the downward. Okay, so basically, you can see from here, we have this upward. Okay, we also have this so over here, sorry, here, this is downward here. Let's say this line here, we have this 3 downward, and we have this 3 line of upward. This is what you mean here. Okay, so basically the end result is that there are actually 3 lines of force pointing upward in the first lambda over 4 distance, and also an equal number of lines that is direct downward in the second lambda over 4. Okay, since there is no net charge on the antenna, the line of force must detach from the conductor and form closed loop as illustrated in the figure here. So basically you can see that they basically form a closed loop. Okay, so basically this is under the so-called the lambda over 2. Okay, so with this, I hope you have a better idea. Okay, how does single wire, 2 wire, and dipole antenna actually release the electromagnetic wave into the environment? Okay, with this, I'd like to end this discussion. Okay, please help to like and subscribe. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you.